So for question number 7, it says answer the following questions that relate to the chemistry of nitrogen. So 2 nitrogen atoms combine to form nitrogen molecule as represented by the following equation. Using the table of average bond energies below, determine the enthalpy change delta H for the reaction. So remember, because we're using bond enthalpies, we need to do reactants minus product. So if you look at your reactants, you just have 2 nitrogen atoms. So you don't need to break anything because they're already separated. But then you do need to form N2. So if you draw the Lewis structure for N2, it's going to be a triple bond. So I need to form that triple bond. So it's just going to be the negative of the bond enthalpy, which is the energy required to break it. So it's going to be negative 950 kilojoules. All right? And so you get 1 point for the correct sign, which is negative, and 1 point for the correct value, which is 950. For B, the reaction between nitrogen and hydrogen to form ammonia is represented below. Predict the sign of the standard entropy change, delta S, for the reaction. So let's figure out really quickly. It says predict, so it doesn't want you to calculate it yet. But if you look, I've got 4 moles of gas on my reactant side, and I have 2 moles of gas on my product side, which means that my entropy, or my disorder, is decreasing because I'm going from 4 to 2 moles of gas. Therefore, I'm going to predict that my entropy is going to be negative, and that's because I have fewer product molecules than reactant molecules, meaning I'm going from 4 molecules of reactant to 2 molecules of product, and specifically they are gases. So you get 1 point for saying that it's negative and 1 point for noting that you have fewer gas molecules in the product side. Okay, for C, it says the value of delta G for the reaction represented in part B is negative at low temperatures, but positive at high temperatures. Explain. So I need to show my Gibbs free energy equation, delta G equals delta H minus T delta S. Okay. I know from the problem that my delta H is negative and my delta S is negative. Therefore, the only way for delta G to be negative is at low temperatures, since delta S being negative would make the negative T delta S positive. Okay, so at high temperatures, the T delta S would cause the delta G to be positive. Okay, so it's a battle between your entropy and enthalpy right now. So some way of explaining that, the fact that your delta G would be positive if temperature were too high because your delta S is negative, would work. So you get 1 point for using that equation and using it to explain why delta G would be positive at high temperature but negative at low temperature. So 1 point for that. In D, it says when N2 and H2 are placed in a sealed container at low temperature, no measurable amount of NH3 is produced. Explain. So I assume your temptation would be to say, well, this isn't a spontaneous reaction, so nothing's going to happen. But it is. We found that delta G at low temperatures is spontaneous. So the issue now is that it is just really slow. Okay? So you don't think anything's happening, it's just because the reaction itself is so slow. Well, why would it be so slow? Well, it would be so slow if your temperature is really low. Remember, your molecules are not going to be colliding with one another very frequently or with a lot of energy, right? And so it's unlikely that they're going to collide with enough energy to overcome the activation energy. Okay, so you're going to have fewer collisions with less energy, and therefore the reaction rate is going to be very low. Okay, so you get 1 point for indicating that the frequency of the collisions is low, and 1 point for noting that there's not going to be enough energy for the reaction to proceed quickly. Okay, so remember, 2 things that really affect the speed of a reaction: the number of the frequency of collisions and the energy of those collisions. If the energy is low, then that prevents the reactions from occurring often because the reactants will not have enough energy in order to overcome the activation energy. So you've got to include the frequency of collisions and the energy of those collisions.